Let's get started. So today we're talking about stream processing in a gaming company. And within this presentation, you will see two things, or you will get out two things. First of all, you will be pumped about doing more stream processing, I promise you that. And secondly, you will also know the similarities between ice cream and gaming. So those are the two things you get out of this presentation. But before all that, let me introduce myself very briefly. So my name is Volker and I'm working for InnoGames, and we are Germany's leading developer and publisher of online and mobile games. But I don't want to bore you too much about talking about myself. Instead, let's go on a road trip. And I'm always doing this because it's a little thought experiment, it's also a little bit interactive, so you will not fall asleep, I ensure that. And yeah, so this whole thought experiment is about going on a road trip, and I would kindly ask you to imagine that you're doing this road trip with your family, so you're driving the car and the family is sitting on the back seat. And to make this a little bit more interactive, and I hope some of you at least will join in, I would like you to really think of sitting in a car and holding the steering wheel like that. So please, at least some of you, put up your hands like this. You're sitting in a car. Maybe you can share a car, so some of you can relax. Anyhow, so you're sitting in the car, you can also do it like this, very cool. Yeah, so you're driving with your family in this car. There's a lot of traffic on the road. You have to concentrate, you have to focus on all the data, information around you. And now I want you to do something weird, because while you're driving, what you now do is you close your eyes while driving. And I really want you to think about doing this, so close your eyes for a second at least. Imagine you're driving in a car, now with closed eyes. Yes, you may open up your eyes again. So how do you feel about that? Maybe someone, how do you feel in the first row? Sorry to ask you, but scared? Yeah. I mean, I can assure you that you don't feel good about it, right? I mean, you feel scared, you feel guilty maybe, because you just put the lives of your loved ones into danger by closing your eyes while driving. So I can assure you that you will not feel good about it. And the question here is, would you ever do that in real life? I mean, it's a stupid question. The answer is no, obviously, hopefully. And of course, this is a metaphor. And the metaphor here is that the car is your team, your project, your company you're working in, and the passengers in the car, those are your co-workers, your colleagues, your team, basically. And all those signs, traffic lights, the instruments in the car, the other cars, all that is the data that is flowing around you that you can look at while driving the car. And now the question is, again, in a metaphorical sense, would you ever do that, closing your eyes while driving? Well, the answer should still be no, but unfortunately, a lot of people do that. So they close their eyes and they hope for the best, and also they do not look at all the data that is around them, make use of them. You have to process data on time as it happens. That is the message here. And also, batch processing might cause accidents, to stay in this metaphor. Because some people, what they tend to do is they drive the car and they open up their eyes once a day or once an hour, and they look at everything that happened, and they then try to fix how they drive, but this also doesn't work out well. So batch processing might cause accidents in this metaphor. Because, and I think this is one of the most important messages out of this talk, it is that life doesn't happen in batches. And this is a quote by Alan Friedman and Ted Dunning, two great speakers, and they also have a free ebook. I put the link in the slides, and I think they will be published afterwards, so don't worry, you will get them. They also explain a lot about this motivation. I think it's a very, very important quote. Life doesn't happen in batches. And this is one of the motivations why I think it's so important that we also think about stream processing and integrate that into our whole infrastructure. Okay, my second motivation, and my promise that I made you, is that I will talk about ice cream and gaming. So what do those two things have in common? First of all, both of them make us happy, obviously, hopefully, especially when it's warm outside. And there's another similarity. So I have another question to you. It's becoming interactive again. What do you think? Which of those two ice creams tastes better? So who thinks the one on that side? On the very that side. Okay, lots of hands. I think so too. But why? I mean, you can't know. You just judged it by how it looks, and you think, okay, this looks like it tastes better, I want to get that one. And the thing is, this is called the so-called halo effect. And this is something where ice cream and gaming have some important similarities, because the moment a customer enters the ice cream shop and he sees all the ice cream over there, well, he will decide if he likes the ice cream, if he buys it, maybe how much he will buy. And on the same side, when the player downloads the app in the App Store and opens up the app for the first time, is playing his first session, he will decide if he comes back, if he wants to pay for the game, if he likes the game. So the first session is crucial. This is very important. And the thing is, if you do only batch processing and do not react to user interaction in real time or very fast, then you will miss the chance to interact with the player in his first session. So maybe if you process the data every night, the next day you will find out, well, those players churned in the first session, but you can't do anything about it anymore because the first session is already done, basically. So in order to make a positive impact, a response needs to happen quickly. This is the message here. And this is also known as the time value of information. So information does not only have value, I mean, it has value, obviously, depending on what you can do with it and what kind of information you get out of it, but also it has a time value. That means that the information that you have gets less valuable over time. And there's even an app called Vase. I don't know, do any of you use it or know it? Hands up if you at least know it. Okay, a lot of you. So it's pretty cool because it's a crowdsourced navigation software, so to say. And what it does is it gives you navigation information and also information like speed traps, traffic, or gas prices in real time. And what you do as a user is you put in user reports in real time. And then they have a cool processing pipeline where they process this data and give it back to the other users. And this is only based or possible based on the time value of information. If they only would do batch processing, well, then you get reports like, by the way, 10 hours ago while you were driving on the road, there was a speed trap, just that you know it. So it's not very valuable for the user anymore. Okay, so respond to life as it happens. This is the important message here. And this is why we do stream processing and why I like to talk so much about stream processing. And if you think about it, every kind of data that is generated is kind of a stream. So no matter if it's GPS data, web page interaction, or maybe also sensor data, everything is related to time. And in its origin, it's some kind of stream of data. And stream processing is now nothing else than processing data in motion. And if you look at it from a more technical perspective, it means that you have like a source of data and like a source stream. You have an operator, this is normally where your streaming code lies, and also you have a data sink, so an output stream. You can also have multiple ones of those, but this is more or less how all the stream processing applications look like. And what changed over the last decade is that, I mean, stream processing is not new, to make that clear. Stream processing has been around forever. So in the car industry, all those driver assistance systems, they need stream processing, of course. They need to process the sensor data and give feedback to the user. But stream processing has become much easier also for a broader range of companies to use. And you see here just a fraction of all those technologies that are out there that you could use for stream processing. And there's pretty cool stuff like Kafka Streams, for example, that is doing stream processing right there where the stream lives, basically. You have Apache Spark, which is quite fast and also has a micro-batching approach. You have Apache Storm, like the godfather of open source projects for stream processing. Or you have stuff like Apache Beam, which is basically a layer on top of that, where you have a domain-specific language to define your stream processing application, and you can then let it run on, for example, Flink or Storm. But today, I will focus on the squirrel. So this is Apache Flink, obviously, because this is also what we use at InnoGames. And I wanted to introduce to the technology just a little bit. So Flink is a framework and distributed process engine for stateful computations on unbounded and bounded streams. So this is what the definition says, at least. And I will explain it to you by explaining those three main components, so to say, of Flink or stream processing in general. And I start with everything as a stream. So an unbounded stream is a stream of data that has a defined start, but no defined end. So it's continuously going. And a bounded stream has a defined start, but also a defined end. And this might sound familiar because this is also known as batch processing. So also batches of data can be represented as a stream, obviously, but with a defined start and end. So everything in Flink is basically a stream. Now the next concept is time. And time is very important because if you have time in batch processing, in the batch processing world, it's easy to deal with. You can just reorder your data sets, you can order it however you like, but the issue is in stream processing is not so easy to do that. So you have to decide between different concepts of time, basically. And the Star Wars example is pretty cool to explain it, because if you order the Star Wars movies by the so-called event time, you order them by the time what happened in the movie, so how the story goes, like episode 1, 2, 3, 4, 5, and so on and so forth. On the other hand, if you go by processing time, means when the movie was processed or created, then the order looks different. So we start with 4, 5, 6, and then 1, 2, 3, and so on and so forth. So it's a major difference in the order. And Flink has possibilities to deal with time and also to deal with so-called late events. So it will put the events into the right order for you. The next major concept, and this is like streaming 101 basically, it's windows. So usually if you have, for example, a sensor that generates data every second, you don't want to process one value at a time. Instead, you want to look around it and also process other values, a set of values. And in this case, imagine you have a sensor generating a value every second, and then you can have so-called time windows, tumbling windows in this case, which will group together by 4 seconds in this example. So you have sensor data of 4 seconds, and every 4 seconds you can apply an operation to your window. In this case, we are summing up the values simply, so we get a new output stream, and every 4 seconds, this output stream has a new value for us. The next window is the so-called sliding window. It is very similar, but instead the window is moving with the data. That means that you get more output values, but also it means that you process some of the data points multiple times. And depending on your use case, you want to use one or the other, of course. There are also more advanced windows, for example, so-called session windows in Flink. And this is pretty cool because if you imagine you have a web page, like a web shop, and you want to track like all the events together that belong to a user session, but you don't have a clear start and end of a session. And what Flink is doing then, it will find gaps between those events. You can define how big those gaps should be, and then it will group together those user sessions. It's a more advanced concept, but it's also working pretty well. Yes, those are the main concepts in Flink, and now you have building blocks to create streaming applications. And basically, you have 3 main building blocks. You have data sources, so where does the data come from? You have transformation, you want to transform your data in one way or the other. And you want to have some kind of output, data sinks. And then you have APIs to work with those building blocks, to define them, to create them. And those APIs are different in the sense that some of them are more expressive and the other ones are easier to use. And you should, just look at this chart. It will show you the different layers of the APIs that Flink offers. And on the very bottom, you have the process function where you have all the power. So you can do basically everything. You can implement your custom streaming application in Java or in Scala, also Python. So you have all the features that Flink offers. And then you have the data stream API on top of that, which has basic components that you can use, like a map function or a filter function. And then on top of that, you have the SQL and table API. And this is quite cool. And I want to show you just briefly how it works. What Flink does is it basically takes an unbounded stream or bounded stream, transfers that into a so-called dynamic table, and then you have continuous queries going that will modify this table. And it's not so easy because the concept of having SQL on tables is different from having streams. So it's a bit more complicated. But in the end, what you can do is you can do SQL queries on those streaming tables, on those dynamic tables. And since Flink 1.7.0, you can even do match recognize, which means you can do pattern detection within your stream just by writing SQL. Of course, all this is not yet feature complete. We are also not really using that right now, but it's pretty cool to play around with. And I think if this gets developed further, then it would be pretty cool also for data scientists to just easily write SQL queries on streams. Yes, let's have a closer look on how you usually write Flink applications. So this is a simple Flink application. It has a data stream just with 4 elements, 1, 2, 3, 4. And it has 2 transformations applied to the stream. First of all, we're applying a map operation, means we're taking the input element and creating a new output element. We take in an integer and creating an integer by just adding the number 2. Very simple. Then we have a filter operation, and in this case, we only want those elements who are divisible by 2. And then we have our data sync. In this case, this is a print function, which will just output the stream to the standard output, and then you can see it. Very simple. Now we have our Flink application and we want to deploy it somewhere, somehow. And for that, there's a Flink runtime. And also that is quite flexible. You can have a standalone Flink cluster. That's what we do at InnoGames, for example. You can also use your Hadoop resources and let it run in Yarn. Or you use Mesos and Kubernetes, and then you are even more flexible. And the Flink runtime, it's kind of magic. So it's very good in hiding its internal details, and I don't want to go too much into it. So I will just take you a little bit into the rabbit hole and show you the basics of the Flink runtime. So this is how it looks like. It might look a lot in the beginning, but let's start at the very top. So Flink first tries to chain your operators. So this is again the application I showed you before from the example. It tries to chain operators if it makes sense. You can also control this chaining a little bit, but Flink will try to make it as good as possible so that the network overhead is as little as possible, of course. Then it will put those operator chains or single operators into so-called tasks. And depending on your streaming application, it will create so-called subtasks out of it. So it tries to partition your stream. And this is something you can also control. You can say, hey, I want to split my stream by country, for example, and then you have a stream partition per country. And then it's important to know that you have one job manager who's doing all the magic for you, and you have multiple task managers. And each of those is a JVM. And each of those subtasks is basically a thread within such a JVM. And this is how it looks like if you deploy it in a cluster, basically. This is just a rough explanation. Of course, if you want to read more, there's a good documentation about it. But now I want to come to the part how big data and streaming looks in a gaming company and how we use all that in practice. So first of all, a few words about InnoGames. So we are founded in 2007. We have like 7 live games with more than 30 language versions. And yeah, we're coming from Hamburg and we are quite successful in what we're doing. And what we do is mainly data-driven. And this is just a portfolio of our games. And all those games, they basically create data, of course. And this data needs to be processed. And before I go into the technology, I would like to mention the team behind it. Because for me, big data is also about being cross-functional. Because it's different from, let's say, old school software development projects. If you have a big data project, you have different roles and you need to be cross-functional. You need to work as a cross-functional team. And this is also a big challenge. And I don't know if any one of you plays like team games online. There you also have different roles. And if you don't have a good team with all those roles, well, you will lose, basically. And to take it further in this analogy, we at InnoGames, we have, for example, a business intelligence team taking care about making the data available for the people. We have data engineering, that's what I do together with my team. We have data scientists, and we have also operations who keep everything together. And you need all that to process the data and do cool big data projects, basically. So everything I show you now is not something that I did on my own. It's more like a team thing, a cross-functional team thing. Yes. So at InnoGames, we have a so-called event tracking, which means that if you play the game, you will interact with the game, and while you're interacting with the game, we will create so-called events. And those events are tracked centrally in a centralized way, and we have currently over 1.5 billion of those events per day. Yes, and we process all that with our data architecture, and I always like to split it in 2 parts, the data pipeline and the data platform, basically. The pipeline is the fast streaming thingy that is processing data in milliseconds, seconds, or minutes. And the data platform is basically doing the heavy work and processing hours, days, or years of data. And for those two components, we have two main technologies driving all that. And in the streaming part, it's basically the Squirrel, so Apache Flink. And in the data platform part, it's obviously Hadoop. In this case, we're using Cloudera on CDH5. And this is how it looks like a bit more in detail. So on the very left-hand side, you can see that we have so-called event clients within our games. And they send those events to a so-called event gateway, which is the entry point to our whole architecture. Then we have our event bus, which is a stream representation of those events. And this is also where we do stream processing, obviously. Then we have our distributed data store, and this is where we do batch processing. And then, very important, we also have a business intelligence system. And this turned out to be something pretty cool, because combining the power of Hadoop with some classic business intelligence system like SQL Server works really well for us. Technology-wise, yeah, we're using a lot. We are using Go for the clients. We are using Dropwizard, Flink, Kafka, Scoop, Hadoop, Spark, Hive, Jenkins, SQL Server, and a lot more technologies, basically. And I could talk about each of those for hours, but we need to focus. Otherwise, I will not finish in time. And we focus on the streaming part. And I brought you some of the streaming use cases that we actually implemented, because I thought it might be interesting for you to have a look how it looks like in practice instead of doing word count for the 1,000 times or I don't know what. Okay, first use case is event metrics. I like this one because it's so simple and it generates so much value within the company. So this is the whole application, the whole streaming application. Well, there's a bit of glue code around it, but this is the whole business logic. So we have the stream of events, and what we do here is we map each stream event to a tuple, whereas the first element of the tuple is just the event name, like build or fight or whatever. And the second element of the tuple is number 1. So indeed, it is kind of a word count example. Then we do a key by 0. This is very important. So we split the stream by the first element in the tuple. This is where we generate parallelism in the cluster, because we say, okay, every stream partition should be per event name. So every build events go into the same stream partition. Then we do a time window of 1 minute, and then we just sum up the second part of the tuple. And then we have a graphite sync. And what we can do then is generate graphs like this that are updated in real time. And then, for example, the game designer can see, okay, how did the interaction with the games change after deploying something in the game? And maybe, as you can see, there's a spike in fight events. Maybe something changed over here. So they can directly see not only technical metrics, so to say, but also game-specific metrics, how users interact with the games. The second example is the log00 monitor. It's a bit more complicated. So let me explain what the purpose is. If you download an application, like the game, you register for the game, and after that you should end up in the game. So you should log in. So after each registration, what you expect would be a login. If you don't get a login, something went wrong. Maybe, I don't know, the player dropped the phone while he was registering for the game. I don't know, something like that. So it's definitely wrong if you don't have a login after registration. So this monitors how many times this happens. And I show it to you step by step. First of all, we only filter for registration and login events to make it smaller. Then we do key by player. So everything from the same player goes into the same streaming partition. And then we do this. This is also a cool feature. This is now pattern detection, but not in SQL, but in code. And it's also not that complex. So we are looking for a pattern within the stream that starts with a registration, is followed by a login, and this should happen within 60 seconds. And then we are sending timeouts and successes both to Graphite again. And then we can create dashboards again that look like this. So the yellow line on the bottom, this is what we want to have very low, because it means no login within 1 minute after registration. And the green line, this is something you want to keep up high. This means the player also logged in within 1 minute after registration. So very simple case of pattern detection, but also very powerful. The next one I will just briefly explain, because it's a bit more complex. It's called near-time CRM. And what it means, very briefly, it means based on the user interactions, we are able, with our stream processing capabilities, to react to his interaction with the game. And we do this mainly by showing so-called interstitials, and you can imagine them as like little pop-up messages within the game. So all this happens within less than 10 seconds, and this is basically a delay that we can also reduce still. And one example is within the game Elvenar, where you have resources to build your buildings, and there's some special resources that are not so easy to get, and you need to use a feature that you get later, which is called the trader. And some people, they use it, but some people, they don't use it, don't get the resources, and they churn from the game. And with stream processing, we're able to see if they use this feature properly, and if not, they will get just an interstitial like that that explains it more. So by doing that, we are also taking stream processing in a way so that we directly interact with our products. And this also, reduces the churn factor, so it's a good thing, of course. Yes, and now I brought you a little demo. I hope it works. You can also check it out on GitHub afterwards. And this shows you a little bit what you can do with Flink very simply. And I hope you can all read it, right? Also in the back. Is it fine? I hope so. Good. So this is a Flink application running on my local machine. And what I did here is I defined a stream, and I added a so-called volume level source function, which is something that I implemented on my own. So it's very easy to also generate own sources. And it reads the microphone sensor of my my laptop, and it will generate like volume level objects out of it as a stream. And this stream has a map function, and what it does is that it only gets the amplitude of the volume level object. In other words, after this step, we have a value that is representing how loud it is in the room, basically. Then I do a time window of 3 seconds, and I'm getting the maximum value that I found in this 3 seconds, and I print it out, basically. And this is executing it on my laptop. Now I'm doing this, and I hope it works. So what we should see now is every 3 seconds, we get the maximum recorded noise level in the room. And yes, now I have to ask you for a favor. I have to ask you for some noise, or applause should be fine, so that I can see how loud you can be. So I know as a speaker you should not ask for applause like that, but it's for demo purposes, so please do it. Okay. Ooh. For a second I thought you crashed the application because you're being so loud. But okay, this looks already quite good. I need that value for the next demo, so okay. Anyways, let's get to the next demo. And this one looks more complex, but it's not in the end. So we have our stream again. We have the map function, the same map function as before. We have again our time window. And now we apply a custom window function. And this shows how easy it is to implement custom window functions, basically. And also it shows another feature that is called state, because you have states that are bounded to an operator. And I use it in this case to store a Boolean value. And now the apply function is called when the window is computed. So after 3 seconds, this apply function is executed. And now I'm getting the maximum value out of this time window on my own. Very simple. And then I have this if clause, which is basically saying, if you have not yet triggered and the maximum is above a certain threshold, you want to collect a new output element. So this is the output element, and we collect it to this out object, which is the collector. And this is basically representing the output stream of this operator. So everything we throw into this out.collect will be the output for the next operator on the stream. Then there's some glue code or config code. Don't worry about that. And then we have here another sync. In this case, I also implemented one sync on my own. Also, that is quite simple, and then we execute it. So since you were quite loud, I will increase this. That should be fine. So let me put my Twitter account left to it, because we need that. And hopefully, if it works, the streaming application should put in a tweet for us if you are loud enough. Let's wait for a second so that it's started. Okay, now it's your turn again to be as loud as you can. So give it a try. Okay, thank you. It worked, as you can see. There the tweet popped up. Whew. Very good. I think that was really loud, but yeah, very cool. Yeah, so it shows how simple it is to implement your own streaming operators. And this is basically also what we use to do this whole CRM stuff, so it's very simple to also connect it to your systems that way. Okay, back to my presentation. Now, I want to summarize a little bit. First of all, feedback is appreciated. I really am a big fan of feedback, so if you have something to improve or if you like the presentation so far, just let me know, please. Also, I always like to share knowledge. If you have some cool streaming experiences or something you want to share, just also let me know. I'm very keen to talk to you then. And yeah, this is something you should take out, so life doesn't happen in batches. I'm not saying that batch processing is necessarily bad. I know it's a very important part, but we should not forget about stream processing. And yeah, eat ice cream and stream on. The weather is good, I think. I don't know, but I think it's pretty good. And there's also great Flink training that are linked in the presentation that you can check out. Yeah, and that being said, thank you very much. Have a great conference and good lunch. Yeah, thank you. And if there are any questions, you can also ask them, because there are two microphones over there, and I think we have at least 2 minutes left or so. I don't know, but doesn't look like it. Ah, there's a question. Directly at the microphone. Perfect.
On your architecture picture, you also had Apache Spark. And
yes.
I suppose you expect this question. Can you elaborate a little bit on the differences between the two?
Sure. So yeah, we also use Spark, but we use it in the batch processing way. Yeah, so Spark is also having similar streaming concepts, similar feature set. It's doing a micro batching approach, so it's also allows you to do stream processing as Flink, but with micro batches. That you can reduce the batch size, of course, but this will also have an impact on your throughput, obviously. Yes, so this is one of the differences. It's very well integrated to the Hadoop environment. That is also a pro, because running your Flink cluster on Yarn has some disadvantages. That's also why we don't do it, because it also interferes with the other applications running and you cannot control it so good. But yeah, in the end, we decided to go for Flink, but we also use Spark, but only for batch processing in this case, because it works really well for that case. Yes, another question next to it.
What are the pitfalls you have encountered with using Flink? Issues around setup or scale? Anything?
Issues with Flink? None so far. No, I don't know. It's hard to tell. I mean, one thing is that we can't use our resources so well, so the integration into Hadoop could be a bit better. This is something that we discovered. It would be cool to have more control over how it affects other processes in Yarn, so the resources that it uses. Yeah, apart from that, it's hard to tell. I mean, one thing is, of course, also that you have slight delay, because your stream most likely lies in Kafka, and you have to copy it over, basically, so you have to have network delays in there. You can get rid of it if you use Kafka streams, for example. It's a cool alternative for that. But on the other hand, network connections are so fast that we don't see it as a big issue so far, so yeah.
But you have not had issues with scale, handling scale
no,
in terms of volume?
Not so far. The thing is, 1.5 billion is quite a lot, but I mean, we can manage it with a rather small cluster so far, so it's like we don't have big issues so far. Thanks. Yeah. Maybe the microphone so that people can hear it. I can also repeat the question, but I think it's...
So at the beginning, you listed the stream applications we have around, and at the architecture diagram, there was Kafka and an arrow to Flink. So why do you need both? Or what's the reason for that?
Why we need Kafka and Flink is the question, basically.
Together, yeah.
Together, okay. Well, by the time that we started with it, I mean, we started off with Apache Storm, and we also not started with Flink, but with Kestrel. It's not that famous anymore, but this is how we started off, with Kestrel and Storm. And then we later on switched to Kafka, and then we switched Storm to Flink. And by that time, also Kafka Stream was not that mature as it is right now. So it's a matter of how our systems evolve, because we did not use Kafka all the time, but Kestrel in this case.
Basically historical reason.
Yes, that's true.
Okay.
But yeah.
Thanks.
You're welcome. Yes, there. Whoever.
Are there any downtimes when you deploy a new version? If yes, how do you deal with that?
Downtimes when we deploy a new version of the Flink applications, you mean? The good thing is that Flink has this checkpointing algorithm that allows you to ensure that you don't lose data, but also it ensures that the data that is incoming affects the outcome exactly once. So it doesn't mean that everything gets processed every once, but the outcome is affected exactly once. So we have a little downtime, but in those cases it's fine. Also, like for example this CRM thingy where we interact with the players, there we have a mechanism that says if the delay is above a certain threshold, we will not interact with the player anymore. So if we trigger an interstitial and we see, hey, this would be for something that the player did 10 minutes ago because of the downtime that we had, then we will just not trigger it. That is fine. So yes, we have downtimes. But
Do you know if it is possible to overcome it? Not to download?
good question. I don't know, but maybe someone knows the answer.
The data to be buffered, then the Kafka stream and of links updating
Yeah.
data still there, and then the link starts again, then insert the data. So this doesn't go to
Good point. Thank you. Another question over there.
How do you
Replicate
replicate state?
state. So Flink does have various state backends that you can use, and by that you can also configure on how you want to replicate it. So not sure what the default configuration is, but you can configure that. Okay. More questions? Oh, there. Yes.
I had a follow-on question to the first question, actually, with the comparison of Flink and Spark.
Okay.
Like one of the problems that you see in Spark is that you have micro-batching, which is understandable. But when you're talking about these windows, like you're
Yeah, sure.
kind of
It's
winning in a batch anyway.
that is correct. Yeah. So yeah, also this argument about micro-batching does not always count because you're doing windowing anyways. But for example, with the CM interactions that we do, we react to one event at a time, and this is something where we need real stream processing. On the other hand, I'm sure you could also do this with Spark in a way so that we don't lose so much. But to be honest, also with the development of Apache Beam, I think it's clear that it doesn't matter so much anymore what kind of technology you use underneath, because the basic concepts, like the code that I showed, looks rather similar to what you can do in Spark or, for example, in Storm or whatever. So the concepts are basically the same. And I think looking at something like Apache Beam is pretty cool because it shows it doesn't matter so much anymore. So, yeah. Yes?
So I guess the reason why you are not using Beam is because of maturity at the time of you started?
Correct.
Okay.
That's correct. But yeah, I'm looking into it, so maybe next thing. Yes, over there.
You mentioned that you built a lot of dynamic tables off of the output of your processing, and I was wondering whether you do the synchronization on the Flink processing level, if you're trying to synchronize multiple events happening together, or you do the synchronization at the syncing level of the data.
So what I showed you was the dynamic tables. This is something that we unfortunately not yet do. But the syncing, what we do, I mean, if I got it correctly, we do it at application level, so in our custom applications. Does that answer your question? Not sure.
No, my concern is if we have
Yeah.
if we're doing the same multiple processing for the same data source,
Mm-hmm.
and I'm trying to synchronize the output of these so that they concurrently sync into the same data sync. Are you doing the synchronization on the events level, or are you doing the synchronization on the syncing level? Or like how do you do this?
The thing is, this is kind of, if you have to think about how to do the stream partitions. So what we do is we do the syncing basically by streaming or by partitioning the stream by the players, and this way we have the possibility to scale very well because one player does not have so many events, and the order is guaranteed for this stream partition. So we do it at that level. Okay. Yeah, I don't know. Yeah. Okay.
Still about scalability. You mentioned you have different use cases.
Yes.
Are they all consuming from Kafka at the same time? And how you intend to scale for 100 use cases?
Well, good question. In the end, what we do is we have one main topic in Kafka that contains all the data that is valid. So we do some kind of validation before to ensure some kind of data quality. And then what we do is either we consume from that topic, or if we have special use cases, we copy over it within Kafka. So we create a new topic that is just a copy of the other one. It will add a slight delay, but then you're much better in case of scalability. So that's what we do. Cool. And another one.
What size of Kafka cluster?
What size of Kafka cluster? Good question. I think we're only at 7 nodes so far. 7
nodes?
Yeah, 7 nodes.
Okay. And one more question. Flink and Spark Streaming, they can be compared?
Yes, they can be compared, right. So, I mean, they're very similar also in the case of the things that you can do. The feature set is very similar. I would say how underneath how it works is a bit different. You can run them on similar platforms, so yes, they're very similar. But again, like I said, it's almost a matter of taste what you use, because with applications like Beam, you can even choose what you want to use in the end. Yes. Okay. More questions or lunch? That is the question. Okay, one more question.
If you don't consider historical reasons and you start now from scratch, what will be the set of technologies you will choose, considering the current landscape?
Good question. I mean, this is a good question, but it's not easy to answer. So if we build it from the scratch, what would we use in the end? I guess that's a question. I mean, the thing is also with InnoGames, we have a history with on-premises. So we have an infrastructure that works quite well on premises. And often it's not easy for us to move to the cloud. So if I personally would start over again, I would more try to use cloud services to be more flexible. And at the moment, I'm very keen to give Apache Beam a try for the stream processing, because it gives more flexibility on what you use. And I would also maybe try to utilize Kafka more by using Kafka streams. And yeah, so this is the thing I would do. And yeah, for the Hadoop part, I would still use Cloudera because it's just working fine for us. And we are at a Cloudera conference, but I really mean that. Okay, more questions? Cool, then thank you again and have a great day.